This is the final video in our discussion of the reactivity of functional groups containing polar pi bonds. And today we're going to focus on or return to alpha carbon chemistry and the alpha carbon chemistry specifically as it relates to esters. So you might already have a guess of what will be happening in this lesson. Our learning goals for today are to be able to explain the relative acidity of various carbonyl containing functional groups. So acidity, alpha carbon. Predict the products of Claisen condensations, including cross and intramolecular variants. Well, cross and intramolecular, that reminds me of aldol, and in fact, Claisen is the aldol reaction with esters. Evaluate synthetic schemes using the alkylations and decarboxylations of 1,3-dicarbonyl compounds. We've encountered 1,3-dicarbonyl compounds before in the context of ketones, and certainly we'll discuss them again today, but we will throw esters in the mix. But esters, first word of the title. We'll predict the products of Haloform, Hell-Volhard-Zelinsky, and Gabriel reactions. So the Haloform and the HBZ, these are alpha carbon reactions, and then Gabriel, I don't know what you want to call this, an alpha nitrogen. We'll show you the Gabriel reaction, and then finally we'll propose curved arrow mechanisms for all of these reactions. 7 reactions for your reaction chart today. Let's get started. Take a moment, pause the video, and propose a synthetic route, so the reagents and intermediates, for the synthesis of this molecule from this starting material. Ready, set, go. You may have recognized, and hopefully you did, that a ketone is converted to an aldehyde in this transformation. The challenge with this transformation is removing the R group from the ketone. It is gone. You have to remove the carbanion, which in this case is the methyl group, and then add hydride. So even though the net transformation represents neither oxidation nor redox, as there are 2 bonds between the carbonyl carbon and oxygen in both the starting material and the product, we recall that to remove an R group, to remove a carbanion, this requires oxidation, and adding hydride will be a reduction. So we remember that aldehydes can be made directly from esters by treatment with dibal at low temperature, followed by an acidic aqueous workup. And that converting R into OR, which makes it a good leaving group, or at least a decent leaving group, this required oxidation. And in the previous lesson, we learned the Baeyer-Villiger oxidation, by which a ketone was treated with a per acid, such as MCPBA, to generate esters. Great plan. It's not going to work. Describe the problem with this proposed synthetic pathway, because it will not work. Good plan, though. It will not work. So pause and write down why it will not. For the Baeyer-Villiger, and there are 2 R groups bonded to the carbonyl carbon of the ketone, we need to identify the substitution pattern at each of those carbon atoms. On the left, there is a phenyl group, and on the right, there is a methyl. And we recall that hydrogen migrates faster than a tertiary carbon, migrates faster than a secondary, which is about the same as phenyl, which migrates faster than a primary carbon, which migrates faster than a methyl. So methyl was the slowest R group to migrate to oxygen during the Baeyer-Villiger reaction. Methyl is the slowest, phenyl is faster. So actually, when treated with MCPBA or another per acid, the observed product will be this one, which is not the desired ester. If this one was reduced with dibal, the leaving group will not be methoxy like desired, which was replaced with hydride in the proposed pathway. The leaving group for the ester that is actually formed is this aryl group. And so if this were treated with dibal, and I'm not going to write it back out, but I'll just color code the arrows orange, it would yield this substituted phenol and acetaldehyde. So a different aldehyde than what is desired. Well, that's a bummer. Should we just give up? No. So we need to learn how to make methyl a leaving group. And this is in the context of alpha to a carbonyl. It's going to be difficult to use Baeyer-Villiger because methyl is the slowest to migrate. And by difficult, I mean impossible. So we need a different reaction. And before we learn that different reaction, let's review the acidity of carbonyl compounds. And I'm not talking here about the acidity of carboxylic acid. That's important. But when we've talked about the acidity of carbonyl-containing functional groups in the past, we've really talked about the alpha carbon. And more of these carbonyl-containing functional groups have alpha carbons than have this carboxylic acid proton. In fact, only the carboxylic acid has that proton, so we do not care about that right now. Remember what we're talking about. We're talking about how to make a methyl ketone, the methyl part, into a good leaving group. All right, so alpha carbon acidity. So what will happen if we treat acetone, this molecule, with one equivalent of a strong base? I'll go ahead and write this out because this should be very familiar to you at this point. If we treat acetone with a strong base, it will generate an enolate and the conjugate acid of that base. I do draw the curved arrows directly to the major resonance structure of the enolate, and I would encourage all of you to try that as well. Sometimes in textbooks, they'll just have this arrow. They'll localize those electrons from the CH bond on the alpha carbon, bringing them to the minor resonance structure. And then they'll show, okay, well, the minor can go to the major. All we need is one extra arrow, and we can go directly to the major resonance structure. And that's what we should do. That's the most precise way to describe the reactivity here. I believe in you. Okay, we've learned that several different bases can facilitate this transformation. We've learned that sodium hydroxide and sodium alkoxides can deprotonate the alpha carbon, and they do so usefully in the aldol reaction. Sodium hydride could deprotonate the alpha carbon, and so could lithium diisopropyl amide, LDA. Proton transfer reactions are equilibria, and the extent to which this proton transfer reaction favors the reactants or the products depends on the nature of the base, and specifically it depends on the conjugate acid of the base. So for hydroxide or alkoxide, the conjugate base is an alcohol or water, and these species have pKa's of 16. The equilibrium constant for a proton transfer reaction is 10 to the pKa of the product acid minus the pKa of the reactant acid. For ketones, the pKa of the alpha carbon is 20-ish. So for alkoxide or hydroxide, this equilibrium actually favors the reactants, acetone. But there are small concentrations of the enolate formed, and in the aldol reaction, we saw that was fine. That was perfectly sufficient for the enolate to continue reacting. For sodium hydride, the conjugate acid of hydride is simply hydrogen gas, which we'll just say has a pKa of about 50. It's pretty hard to measure, as one might imagine, which would make the equilibrium constant for the proton transfer involving acetone and hydride as a base on the order of about 10 to the 30, so really favoring the products. And LDA, the conjugate acid of LDA is diisopropyl amine. The pKa of an amine is around 35. So the equilibrium constant for treating acetone with LDA will favor the products and be on the order of about 10 to the 15. All right, so once this enolate is formed, no matter whether or not it favors products or reactants, we know that enolates are nucleophilic, and they're nucleophilic at the alpha carbon. And that's one useful thing about this resonance structure. It shows how electron-rich the alpha carbon is. So enolates are nucleophilic at the alpha carbon. We have previously learned, in fact, that those enolates can be halogenated. We learned this in Organic Chemistry 1. So see if you can recall what the products of each of these reactions would be, and then we'll discuss together. Because alpha halogenation is occurring either via the enol, which will be formed under acidic conditions, or the enolates, which is formed under basic conditions, these alpha halogenation reactions do involve either acid or base. Under acidic conditions, such as when a ketone is treated with bromine, a halogen, in the presence of acetic acid, a mild acid. First, the carbonyl oxygen is protonated in a proton transfer reaction. This generates a protonated ketone, which of course could just be deprotonated to yield the ketone again, but that would be unproductive. The protonated ketone also has a more acidic alpha carbon. The two alpha carbons of this particular ketone are exactly the same because it is symmetrical, right? There's a plane of symmetry right down the middle of the molecule. So either and both alpha carbons can be deprotonated. We will use acetate, the conjugate base of acetic acid. Protonation of the alpha carbon generates the enol. As we know, enols are nucleophilic at the alpha carbon, which we can rationalize through this minor resonance form, where we've pushed those electrons down on the alpha carbon. Now that enol, which is nucleophilic at the alpha carbon, reacts with molecular halogen, which in this case is Br2. So reform lone pair push, the strong carbonyl CO double bond will be formed right there. Those electrons from the alpha carbon attack bromine and break the bromine-bromine bond. So this is an attack on sigma star. Now we can see the alpha carbon has been halogenated. There is a carbon-bromine bond that's been made in this electrophilic addition step. And finally, this protonated ketone can be deprotonated with bromide, acetate, or perhaps another molecule of itself to keep the process going and generate the alpha bromo ketone. All right, so there's the product of alpha halogenation of this ketone. It is the alpha bromo ketone. Now let's look at the next reaction here. So you can see in this reaction, this is not a plane of symmetry for that molecule, so the two alpha carbons are different. And when that's the case, the reaction does proceed via the thermodynamic enol. And then this hydrogen will be substituted for whatever the halogen is. The halogen here is iodine. Let's just zoom in and write that. That for asymmetric ketones, these reactions go via the thermodynamic enol, which is the more substituted enol, which will look like this in the case of this particular molecule. All right, excellent. We've reviewed under acidic conditions, alpha halogenation. So under acidic conditions, alpha halogenation results in a single halogenation at the more substituted alpha carbon. Let's take a look now at what happens under basic conditions. And this is more important for today's discussion, although reviewing both of these mechanisms was a useful exercise. Let's start in the case of the symmetric ketone. Now, under basic conditions, instead of protonating the carbonyl, thinking about the enol ketotautomerization, instead of protonating, the alpha carbon is deprotonated, right? You have a strong base, deprotonate something. Now, of course, the equilibrium constant does favor the reactants here, as we talked about on the previous page when treating ketones with alkoxides or hydroxide, but that's okay. Some enolate is still formed. And this enolate now reacts at the alpha carbon because it is nucleophilic at the alpha carbon with an equivalent of molecular bromine, generating in this electrophile addition step, electrophile adding to a pi bond from organic chemistry 1, an alpha bromoketone. Now, this alpha bromoketone has an electron withdrawing group, and that electron withdrawing group makes this alpha carbon even more acidic than it was before. And so this alpha brominated ketone continues to react. So an enolate is generated again. And it reacts again with bromine in an electrophile addition step, generating this dibromo. And now this ketone has another alpha carbon. And that alpha carbon also has hydrogens, and their acidity is increased by the presence of those two bromines. So under basic conditions, this continues to react until all of the alpha hydrogens have been deprotonated and then the enolate's brominated. So all alpha hydrogens are substituted with bromine under basic conditions. Now you might say, oh, hold up, why didn't this happen under acidic conditions? Well, because under acidic conditions, instead of deprotonating first, like is what happens under basic conditions, protonated, okay? Once the product, the alpha bromoketone, has been made, if you think about brominating again, if you think about substituting for this hydrogen, you would need to protonate the carbonyl, right? Well, so once you have electron withdrawing group, that actually makes these electrons less basic, less likely to accept the proton from the mild acid. So under acidic conditions, the product is actually less reactive than the starting material, so it stops. But under basic conditions, the product is more reactive than the starting material, so it keeps going. All right, and even if you don't understand that explanation, I hate to say this, you can just memorize it. But under basic conditions, all of the alpha hydrogens are substituted with the halogen. All right, keeping that in mind, now predict the product of this reaction. So this asymmetrical ketone with chlorine in the presence of sodium hydroxide. Yeah, there are 3 alpha hydrogens and all 3 will be chlorinated. Whether or not you took Organic Chemistry 1 with me, and this is a review, or you didn't and you're learning this reaction for the first time, make sure you have it, particularly the reaction under basic conditions, and then let's move on. And we will move on to the haloform reaction. So the haloform reaction is going to accomplish our goal of making methyl a good leaving group. Given our discussion of alpha halogenation, pause and provide a complete curved arrow mechanism for this transformation, which does indeed make methyl a good leaving group. In the presence of a base such as sodium hydroxide, the alpha carbons of ketones are acidic. Either alpha carbon can be deprotonated by sodium hydroxide to generate the enolate. But as we see bromide in the product, we'll just start here. This also makes the thermodynamic enolate. However, both alpha carbons can be deprotonated. Recalling the minor resonance structure for enolate, we know that enolates are nucleophilic at the alpha carbon. So this enolate can reform the strong CO double bond and react with an electrophile. That electrophile is bromine. Attack on sigma star Br breaks the bromine-bromine bond and makes a bond between the alpha carbon and bromine. The alpha brominated ketone is even more acidic than the starting ketone due to the effects of the electronegative bromine. So under basic conditions, the other alpha carbon is deprotonated as well. This proton transfer reaction generates another enolate. Keeping in mind the minor resonance structure of this enolate, we know that the alpha prime carbon will be nucleophilic. The strong carbonyl CO double bond is reformed and the alpha carbon reacts with electrophilic molecular bromine once again, generating this dibromoketone. Now, this ketone is more acidic at the alpha carbon than the monobromoketone or the starting ketone, and so it will continue reacting. There are 2 more alpha hydrogens that can be substituted with bromine by the same mechanism. So we're going to just say keeps reacting. And of course, if this were an exam question, you would need to write out all the curved arrows, but it's not. So we're going to fast forward. And once both of those alpha prime CH bonds have been substituted with bromine, what started out as a methyl group, a CH3 here at alpha prime, is now a CBr3 group. Under the reaction conditions of sodium hydroxide and molecular bromine, the carbonyl continues to react. The carbonyl carbon is and has been electrophilic, and hydroxide can add to it in a nucleophile addition step. Now this has been happening all along, but this step is reversible. And so all along, all the intermediates before this fully brominated one, they were undergoing the same addition of hydroxide to the carbonyl. It just wasn't productive. Instead, reform the carbonyl, expel hydroxide, go back here. But once the methyl group is converted into a CBr3, it represents a good leaving group. Now, how do I know? Well, I know the pKa of its conjugate acid, which is called bromoform. And bromoform has a pKa of about 15. What that tells me is that when this tetrahedral intermediate collapses, it could expel hydroxide, whose conjugate acid, water, has a pKa of 16. And certainly that happens. However, it could also expel the conjugate base of bromoform and a carboxylic acid. Now, certainly both nucleophilic elimination reactions occur. So the one that reforms this intermediate, so the reverse of the addition, and then also this one that forms the acid. However, as soon as the acid is formed, recall the pKa of the acid, it's about 5, and it might be a little bit less because of bromine on the alpha carbon. So immediately, in the presence of hydroxide, the carboxylic acid is deprotonated, and it's not irreversible, but it certainly favors the products by a large equilibrium constant. given the relative pKa's of water and a carboxylic acid. And so then this carboxylate could be protonated in a workup step if you wanted to generate a neutral carboxylic acid. But eureka, we've done it. We made methyl into a good leaving group. We converted it into the conjugate base of bromoform. So converted it into CBr3 using this alpha halogenation chemistry that we learned in organic chemistry 1 or we learned today. But either way, that's what we used. Take a moment, be sure that you have got this down. I know it's a lot, looks like a mess. And once you're ready, well, let's practice. Let's predict the products of each of these reactions. Even if you're not quite sure, give it a shot. We observe that there are ketones being treated with sodium hydroxide, a base, in the presence of a halogen, in this case molecular bromine. Just as we saw on the previous slide, where a ketone was converted to a carboxylate, we do expect alpha bromination to occur. So I have identified the carbonyl carbons. I have identified the alpha carbons. Now, some of the alpha carbons do not have alpha hydrogens. For example, there are no alpha hydrogens on that alpha carbon. The same here. However, we know that under basic conditions, all of the alpha CH bonds will be replaced with bromine, just as we saw when we reviewed, and again when we learned the haloform reaction. You can draw in the implied hydrogens if you wish, and then in the product, you should replace them with bromine. So now for the next problem, we see there's a methyl ketone. Now, when there's a methyl ketone, under basic conditions, the methyl group will be converted into a tribromomethyl group, and this is a good leaving group. So for the methyl ketone, we expect the haloform reaction to occur, and the carboxylate is formed. Say, wait, why wasn't the carboxylate formed up here? Well, this is not tribromomethyl. This is dibromoethyl, and it is not a good leaving group. Okay, there must be 3 bromines on the carbon to make it into a bromoform, a good leaving group. And finally, the last reactant is also a methyl ketone, but its other alpha carbon also has an alpha CH, so we do expect a full substitution. So if you'd like, let's just draw out the intermediate before the tribromomethyl leaves in a nucleophile addition elimination sequence. And then as we said, the tribromomethyl is a good leaving group, so hydroxide can add to it under the reaction conditions in a nucleophile addition step, and then CBr3 will be eliminated. Initially, collapse of the tetrahedral intermediate and expulsion of CBr3 will generate a carboxylic acid, but under basic conditions, it will immediately be deprotonated to form the carboxylate product. And if the acid is desired, the carboxylic acid, then just add a workup step. Okay, and then that would protonate the carboxylate, making the carboxylic acid. Okay, so recall that the point of this was to make methyl a leaving group since it was not reactive in the Baeyer-Villiger reaction. So now let's really take it up a notch. So this slide is really about Baeyer-Villiger versus Haloform. So choose the appropriate sets of conditions for each of these transformations. In problem A, we can see that an aldehyde is oxidized to a carboxylic acid. 2 bonds between the carbonyl carbon and oxygen and the aldehyde, 3 bonds between the carbonyl carbon and oxygen and the carboxylic acid. It appears that this bond between carbon and hydrogen is broken. Now there are several ways that we can accomplish this transformation. We can use Baeyer-Villiger conditions, treating with a per acid, such as MCPBA. However, aldehydes can also be oxidized to carboxylic acids under the same oxidation conditions that are used to oxidize primary alcohols all the way up to carboxylic acids, specifically with chromium reagents under aqueous acidic conditions such as dichromate and sulfuric acid, or chromic acid, or potassium permanganate, so under basic conditions. Ketones can be oxidized to esters, either using the haloform reaction or the Baeyer-Villiger reaction. We really need to think about which bond between The carbonyl carbon and an alpha carbon is being broken. And then we can choose Baeyer-Villiger versus Haloform. So for this transformation, the carbonyl carbon bond to the methyl group is being broken. If we were to treat with Baeyer-Villiger conditions, we would not observe the desired bond being broken. We would observe the phenyl carbonyl carbon bond being broken because phenyl migrates faster than methyl. So we can see up here at the top of the screen. So that is an undesired product. In order to make methyl a leaving group, we will use the haloform reaction. So we will treat with aqueous sodium hydroxide in the presence of molecular bromine. That will generate the carboxylate. The carbon-oxygen bond in the final ester product can actually be generated in a number of ways. The first is just simply esterification under acidic conditions. Just as we would convert a carboxylic acid into an ester, we can convert the carboxylate into an ester. However, the carboxylate oxygen is a good nucleophile, so instead of addition elimination chemistry that we've learned about in organic chemistry too, we could just simply use an SN2 reaction and treat the carboxylate with methyl iodide. Either way would form the desired ester product. Transformation C, again we see a ketone being converted into an ester. It's being oxidized, and one of the bonds between the carbonyl carbon and an alpha carbon, which I'll highlight in yellow, one of those bonds is broken. So which of the bonds is broken tells us which oxidation reaction to use, Baeyer-Villiger versus Haloform. Since this bond is broken between the phenyl carbon and the carbonyl carbon, we will use Baeyer-Villiger, since phenyl does migrate faster than methyl, as we described in the previous problem. Pause for a moment, summarize the haloform reaction, so write your reaction chart entry, and just in a sentence, explain why we learned it. Now propose a synthetic route to the desired product from the given starting material. Before I set you on your own here, just recall this is the problem that we opened this segment with. So this problem. Give it a shot. As we described in our initial analysis, the carbonyl carbon methyl group must be broken. So even though overall there is no oxidation, we know that to make methyl a leaving group, to get rid of it, it will require oxidation and then reduction back to the aldehyde. When we first encountered this problem, the only oxidation route to make an alkyl group a good leaving group from a carbonyl carbon of a ketone was the Baeyer-Villiger oxidation. However, aryl groups, phenyl groups, migrate faster than methyl groups in the oxidation. So this ester would have been formed from Baeyer-Villiger oxidation of this ketone. And this pathway is undesired because reduction of this ester with dibal would not generate the desired aldehyde. However, treatment of this ketone under haloform conditions instead makes the methyl a good leaving group, generating a carboxylate intermediate. Recalling the reduction quadrant of the grid, we know that aldehydes come from esters directly with dibal reduction. It doesn't really matter what this R group is, but we do need to specify in the context of a synthesis problem. So we'll just pick a methyl or an ethyl. We'll keep it to just a few carbons so we're not wasting too many when we remove this group in the dibal reduction. To generate that methyl ester from the carboxylate, we will treat it with an acid such as tosic acid and methanol. Of course, as we discussed on the previous slide, we could also alkylate with methyl iodide just in an SN2 reaction. If you rather stay on your carbonyl grid, then just esterification of a carboxylic acid. If you're comfortable using chemistry from Organic Chemistry 1, then you can use SN2. Either way, form the desired product. All right, following dibal reduction of this ester, the desired aldehyde is observed. Excellent. We have solved this synthesis problem. We will move on to another reaction now, but it stays on this theme of reacting the alpha carbon with electrophiles such as bromine. The Hell-Volhard-Zelinsky reaction named after three chemists, forever now onward referred to as the HVZ. It is an alpha bromination reaction, but of carboxylic acids. So let's just take just the slightest time out so I can tell you why this is important before we talk about what it is. So essentially, we're going to be making alpha bromo acids. And you might say, well, who exactly cares about this? And that's a wonderful question, but a lot of people do because these can be converted into amino acids, which of course technically would have the nitrogen and the protonated state and the carboxylic acid and the deprotonated the carboxylate state. So alpha bromo acids can be converted to alpha amino acids. And amino acids are the building blocks of proteins, and chemists need to synthesize naturally occurring and unnaturally occurring amino acids. So this is actually a useful intermediate, this alpha bromo acid, because it can be converted to an amino acid. And then, whatever this chain is determines what type of amino acid is generated. So that's why we're taking the time to learn this. Now, unfortunately, we cannot just treat the carboxylic acid with sodium hydroxide in the presence of bromide. We would be proposing generating the enolate, right? The enolate is the nucleophilic species that would react with electrophilic bromine to generate this carbon-bromine bond. Well, why not, you ask? You just drew the enolate. Well, what proton is more acidic, the alpha CH or the carboxylic acid? Yeah, the carboxylic acid is. So, oops, would not form the enolate. Instead, the carboxylate is observed. And they might say, well, no problem. Maybe we can still deprotonate the alpha carbon with sodium hydroxide. Well, the acidity of the alpha carbon is greatly diminished due to the electron-rich carboxylate. And we know carboxylates are quite electron-rich. They're unreactive with electrophiles. And in fact, the pKa of this alpha carbon is just so high because of the electron-rich carboxylate that the equilibrium constant, although certainly we could deprotonate to make this enolate, look, it's dianionic. Equilibrium constant is just much, 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 much less than 1. So this is not realistic. This enolate is not formed in great enough concentrations to do anything. So basically, this normal alpha-alkylation, we're making this analogy to alpha-halogenation. And for the carboxylic acid, this reaction does not proceed either under basic, as we discussed, or under acidic conditions. So normal alpha-alkylation does not occur. So that's where the HVZ reaction comes into play. So the same carboxylic acid can be treated with bromine because bromine is going to be the active electrophile. Okay, so what's first actually generated is this acid bromide, which has been alpha alkylated. And then there's usually a second step to generate the acid, carboxylic acid. And so it's just hydrolysis of the acid bromide under neutral conditions. The mechanism is similar to what you expect if this were an acid chloride to a carboxylic acid. All right, so again, carboxylic acid is converted with bromine and phosphorus tribromide into an alpha bromo acid bromide. First, the carboxylic acid reacts with phosphorus tribromide, similar to how alcohols react with phosphorus tribromide to generate the acid bromide. This is going to actually form the enol with the byproduct of a reaction between phosphorus tribromide and the acid. So that's actually going to form the enol. And you could draw out all these curved arrows if you wanted to. You know enough to be able to propose this mechanism, or you can check the textbook. And then this enol reacts with bromine to form the alpha bromo acid bromide, right? And we've seen how enols react with molecular bromine previously in this video. And then there's hydrolysis, as we said, of the acid bromide with water under neutral conditions, similar to what we've already discussed in previous videos for acid chlorides to acids. So now you know, this is how we make alpha bromo acids. And the reason we discuss this is because alpha bromo acids can be used to synthesize amino acids. Let's continue on this theme of alpha carbon chemistry. In review, enolate formation. This slide reminds us of two aspects of enolate formation with strong bases. The first is that base choice can determine the substitution of the enolate, so the thermodynamic enolate versus the kinetic enolate. For example, when there's an asymmetric ketone, such as this one. And then the second is that the base choice affects the equilibrium constant for enolate formation. Right. With an alkoxide or a hydroxide base, the more substituted of the two alpha carbons is deprotonated. Technically, probably both deprotonated, but this one will be favored. Equilibrium will be reached because this enolate represents a tetrasubstituted double bond and is lower energy than if the other alpha carbon had been deprotonated. Okay, tetrasubstituted double bond, lower energy than trisubstituted. However, the equilibrium constant for forming this thermodynamic enolate is certainly less than 1. It's on the order of about 10 to the negative 4. The pKa of a typical ketone's alpha carbon is about 20, whereas the pKa of the conjugate acid of T-butanol is about the same as water, so about 16. Okay, so with an alkoxide or hydroxide base, the more substituted of the two possible enolates formed from deprotonating the two alpha carbons of the asymmetric ketone. So the thermodynamic enolate is formed, it's formed with an equilibrium constant of less than 1. In fact, it favors the reactants by about 10,000 to 1. However, for some reactions, it doesn't matter. In the aldol reaction, this is perfectly fine. It reacted with another molecule of itself in aldol condensation. So sometimes the equilibrium constant matters, sometimes it doesn't. All right, when lithium diisopropyl amide is used to deprotonate a ketone, such as this one, there are two key differences relative to when an alkoxide base is used. First of all, the equilibrium constant will be much greater than 1. pKa of the alpha carbon of a ketone is about 20. The pKa of the conjugate acid of LDA is about 35. This is an amine. So this represents effectively an irreversible deprotonation with an equilibrium constant on the order of 10 to the 15. So first, the enolate is favored equilibrium. Second difference is the substitution pattern of the enolate. The kinetic enolate is formed by deprotonation with LDA. That is because LDA is enormous. And so the transition state for deprotonating at the less sterically hindered, the less substituted alpha carbon, that transition state relative to deprotonating at the more substituted alpha carbon is lower energy. Thus, the kinetic enolate is formed. It's less substituted, it's trisubstituted versus tetrasubstituted thermodynamic enolate, but the transition state to form it is lower energy with LDA, so it is observed. So two key differences using alkoxide bases versus a bulky amide such as LDA. However, of course, we did learn that LDA can be used to make even the thermodynamic enolate if you're a bit clever. So it always initially makes the kinetic enolate. But if we use just less than an equivalent of LDA, so 0.95 equivalents for instance, equilibrium will be reached even though initially the kinetic enolate is formed and the thermodynamic enolate will be observed after equilibrium is reached. With that review in mind, let's continue to think about the acidity of the alpha carbon for various carbonyl containing compounds. Take a moment. Review the pKa values for these carbonyl containing compounds. Draw out the conjugate bases, identify trends in pKa values, and then explain them based on chemical principles discussed in organic chemistry 2 thus far. There are a few trends that we can identify. First, let's look at ketone versus ester. We notice that ketones are more acidic than esters. And drawing the conjugate bases for the ester and the ketone will help us to investigate why that might be. We notice that the conjugate bases are electron rich, and the ester has this electron donating group through the pi framework alkoxy, right? We learned when we discussed the electrophilicity, so how reactive esters and ketones are with nucleophiles, so how big that partial positive is on them, that the ketone was more reactive than the ester because even though oxygen is a withdrawing group through the sigma framework, meaning that it is electronegative, it is a donating group through the pi framework. And this is no different for the conjugate base of the ester. The alkoxy group is a pi donor, and so that electron-rich group destabilizes the already electron-rich enolate. We see this trend of ketones being more acidic than esters, even with the 1,3-dicarbonyl compounds. These are called 1,3-dicarbonyl compounds because the two carbonyls have a 1,3 relationship. The keto ester has a lower pKa value than the diester. Okay, so for the diester, there are two electron donating groups that will destabilize its conjugate base relative to the keto ester. The two electron donating groups and the diester destabilize this enolate relative to the enolate of the keto ester, which only has one electron donating group. In fact, we see that for the 1,3-diketone, its pKa value is even lower than that of the keto ester. Its pKa value is 9. So certainly the electron-rich alkoxy groups of the ester destabilize the conjugate base, making it a bit less acidic. We can put in the aldehyde here. So aldehydes, and again, talking about their alpha carbon because the aldehyde hydrogen is not acidic. So the alpha carbon of an aldehyde is even more acidic than a ketone. Okay, it has a pKa of about 18, and that's because it doesn't have the electron donating alkyl group here. It has hydrogen, because even alkyl groups themselves are electron donating through the sigma framework, which is not as strong as being a pi donor where there's resonance structures that can be drawn. We do see this trend. So electron donating groups destabilize the conjugate base, making for a weaker acid. All right, ketones have alpha carbons that are more acidic than esters. And then we see these 1,3-dicarbonyl compounds are more acidic than the single carbonyl compounds. I don't have a word for that apparently. And that is because for the 1,3-dicarbonyl compounds, the alpha carbons are doubly alpha. They're alpha to 2 carbonyls. How can we explain that? Well, the enolate is stabilized by 2 carbonyls, right? We can draw a resonance structure for the enolate. This enhanced stability of the conjugate base for the 1,3-dicarbonyl compound makes it more stable, and a more stable conjugate base means a stronger acid. In fact, these pKa values for the 1,3-dicarbonyl compounds are quite remarkable. Check them out. 9, 11, 13. These carbon-based acids are more acidic than water, and that's due to delocalization of charge in the conjugate base into 2 carbonyls. All right, remember, more stable conjugate bases correspond to stronger acids, and these conjugate bases are so stable that these acids, these carbon-based acids, are even better acids than water. Okay, be sure that you can explain these trends. Keeping in mind these pKa values, imagine that a model of each of these functional groups is treated with ethoxide. Draw out the conjugate base and predict which side of equilibrium will be favored. In other words, will the equilibrium constant be greater than 1 or less than 1? You try. The key to solving this problem is to identify the pKa's of the acids on the reactant side and product side of the equilibrium. The equilibrium constant is 1 times 10 to the difference in the pKa's between the acid on the product side minus the acid on the reactant side. So for the beta keto ester, the equilibrium constant is 10 to the 16 minus 11, giving us an equilibrium constant of about 10 to the 5. So it's greater than 1 by several orders of magnitude. For the diester, the equilibrium constant is 10 to the 3, which again is much greater than 1. For the ketone, however, this is where we see the shift. So the ketone has a pKa of 20. The alcohol is actually more acidic than the ketone. Therefore, the equilibrium will favor the reactants, and it favors reactants with an equilibrium constant of 10 to the negative 4. That is the same for the ester. The equilibrium constant is much less than 1. In fact, it's on the order of 10 to the negative 9, favoring the reactants. And for the nitrile, which is the least acidic at its alpha carbon for all of these polar pi bond containing functional groups, due to the decreased electronegativity of nitrogen and decreased ability to stabilize the conjugate base, the equilibrium constant is on the order of 10 to the negative 15. Now that we've thought about which side of the equilibrium would be favored when each of these polar pi bond containing functional groups is treated with an alkoxide base, right? That's what we've looked at here. When treated with sodium ethoxide, this is an alkoxide base. Let's consider an interesting reaction of esters. Pause and provide a complete curved arrow mechanism for this transformation. The Claisen condensation is like the aldol reaction, but it's with esters. Recall that in the aldol reaction, an aldehyde could condense with itself. So here are two equivalents of that aldehyde in this beta hydroxyaldehyde, where this bond was made. And this happened via the enolate. So under basic conditions, treatment with sodium hydroxide, aldehyde could form the enolate. Enolates are nucleophilic, and they can react with electrophilic neutral carbonyl forms of the same molecule. And after proton transfer, that generated the beta hydroxyaldehyde. So something similar is happening here, but with esters. And of course, esters are different because esters have leaving groups. They're also different because they're less acidic, right? So the pKa of the aldehyde was about 18. It still made this proton transfer reaction with hydroxide in the first step. It still had an equilibrium constant less than 1, right on the order of about 10 to the negative 2. But that equilibrium constant will be even smaller for esters. Okay, so the esters have a leaving group. Also, you notice that the ester here is treated with sodium ethoxide rather than sodium hydroxide. And this is just to avoid any competing transesterification. So what I mean is that if ethoxide from the sodium ethoxide adds in a nucleophile addition step, forming this tetrahedral intermediate, when it collapses, no matter which of the alkoxy groups it expels, either the ethoxide that was initially there or the ethoxide added with the sodium ethoxide, it doesn't matter either way. Expelling one of those ethoxides, since they're the same, just leads you back to the starting ester. So that's what I mean by avoiding transesterification. Let's say that instead of ethoxide, you used methoxide. Okay, so let's just make methoxide here. And so then the tetrahedral intermediate has a methoxy. Let's say it collapses to expel the ethoxy. Now we have a methyl ester instead of an ethyl ester. So just using an alkoxide base that's the same alkoxy group as is on the ester avoids any transesterification, which is what this process on the left side of the screen would represent. So that is undesired. Transesterification is undesired. So we just use the same alkoxide base that corresponds to the alkoxy group of the ester. So going down the productive pathway now, the alkoxide base deprotonates the alpha carbon of the ester to generate the ester enolate and an equivalent of ethanol. Since ethanol is a stronger acid, much stronger than the alpha carbon of an ester, the equilibrium constant for this proton transfer step is much less than 1. However, this enolate is formed in some concentration, and when it is, it can react with a molecule of itself that is still in the carbonyl form, just as what happens in the aldol reaction of aldehydes. An enolate form of the aldehyde reacted with a neutral carbonyl form of the aldehyde. Ester enolates are nucleophilic. They are electron rich. Neutral esters are electrophilic. They are electron poor. So the ester enolate will collapse, reform that strong carbonyl CO bond. The alpha carbon adds to the carbonyl carbon of a neutral molecule of itself. This is a nucleophile addition step. So we can see what is happening to all the carbons. Here are the 2 carbons from the ester enolate. Here's the alpha carbon of the ester enolate. It made a new bond to the carbonyl carbon of a neutral molecule of the ester, and then there's that methyl group. And look what we have here. We have a tetrahedral intermediate. We had one in the case of the aldol reaction as well. But for the aldol reactions of aldehydes and ketones, there were no leaving groups in the tetrahedral intermediate, and so it just stopped at the beta hydroxyaldehyde or underwent E1CB to make the alpha beta unsaturated aldehyde. However, for the ester, there is a leaving group. And we said that at the beginning. That's one of the big differences between esters and aldehydes or ketones. So this tetrahedral intermediate can actually collapse to reform the strong CO double bond and expel a decent leaving group, ethoxide. This nucleophile addition step generates the 1,3-dicarbonyl compound, the beta-ketoester. Okay, so we can either call it a beta-ketoester or we can call it a 1,3-dicarbonyl compound, because if we number the carbonyls have this 1,3 relationship. Okay, we're done, right? Well, no, because we haven't formed this yet. So what's going on? Well, these 1,3-dicarbonyl compounds, which have this doubly alpha carbon, the alpha carbon, carbon 2 is alpha to 2 carbonyls. They're quite acidic. And we just spent a bit of time talking about how the pKa of this carbon is quite low. It's more acidic than an alcohol. So it has a pKa of 11. So in the presence of ethoxide, which is the conditions we're under, that beta carbon is deprotonated. And this is the first time where we definitely know that a step has an equilibrium constant much greater than 1. And that's because this deprotonation generates the enolate. And I can color code the atoms again so you can see them in the enolate. So it generates the enolate and a molecule of ethanol. This step has such a large equilibrium constant because ethanol has a pKa of 16 and the beta-ketoester has a pKa of 11. So the beta-ketoester is 5 orders of magnitude, 5 powers of 10 more acidic than ethanol. So actually this last step to generate this very stable enolate is the driving force for this reaction. This series of steps would have equilibrium constants less than 1. That's no big deal. So for the Claisen condensation, there's a step 1, treat with the alkoxide base, and typically in the presence of the conjugate acid as the solvent. And then step 2, an acidic workup. And that acidic workup generates the neutral beta-ketoester product. We'll look at another example once you feel comfortable with this slide. And this next example will demonstrate how this last proton transfer step to generate the enolate of the beta-ketoester is so important for this Claisen condensation actually occurring. Let's imagine that this molecule was a desired synthetic target. And you said, oh, awesome, this is a beta-ketoester, so this can be made in a Claisen condensation. Right? To recognize the aldol reaction, the condensation of aldehydes and ketones, we looked for either beta hydroxy ketones or alpha beta unsaturated ketones. And once we recognize them, we would say, all right, well, I know the bond was made between the alpha and beta carbons. So this aldol product must have come from the self-condensation of acetone. You want to be able to do the same thing, so go through the same mental exercise for the Claisen reaction. You want to recognize this time not beta hydroxy ketones, but these beta diketones. And again, it's the bond between the alpha and beta carbons that was made. The tricky part is, though, that the beta carbon, the one that came from the neutral carbonyl compound, and the Claisen, it would have a leaving group on it, right? So it had some alkoxy group that left. So what we would imagine happening here in that Claisen is that this enolate attacked a neutral compound of itself. This carbonyl carbon of the neutral compound becomes the beta carbon in the product. And here's the key carbon-carbon bond forming step. Okay, then the nucleophile elimination occurs to expel ethoxide just as we showed down here. Okay, so you can go through and draw the whole mechanism yourself if you need to. We're just thinking about retrosynthetic analysis. And we did the same thing with the aldol. So you would imagine, I just said, okay, it comes from acetone, but you want to, the analate of one acetone molecule attacks the neutral form of another. All right, so keep all of that in mind. And now we'll think about why this Claisen condensation is actually unfavorable. And it does occur. So if you were to treat this ester with sodium ethoxide, it does occur. But this product cannot be isolated because the overall equilibrium constant is much less than 1 for this process. Let's see if you can propose the mechanism for the Claisen condensation here. It's the same steps as what we just did in this problem, with the exception of one step that cannot happen. Spoiler. Okay, pause and give it a shot. In the presence of this strong alkoxide base, just again noting that the alkoxide chosen is the same as the alkoxy group on the ester to avoid any transesterification in the product. The alkoxide base deprotonates the alpha carbon of the ester. This proton transfer step has an equilibrium constant much less than 1, on the order of about 10 to the negative 9. And generates the ester enolate, which is a nucleophilic species at the alpha carbon, and ethanol, which has a pK of 16, which is why this step is unfavorable. The ester is the weaker acid in this proton transfer step. Now, the ester enolate reacts with a neutral molecule of itself in a nucleophile addition step. The nucleophile addition step results in this tetrahedral intermediate. Let's map on the carbons together. In green are the carbons of the electrophilic partner from the Claisen condensation, the nucleophile addition step. In red are the carbons of the nucleophilic partner of the same step. Here's the alpha carbon, and this is going to become the beta ketone. So now, because the ester does have a leaving group, here it is. The ester that was attacked is going to expel that leaving group. So collapse, reform the strong CO double bond in a nucleophile elimination step, and expel ethoxide. Well, so far so good, right? It looks like we formed the beta ketoester. Well, we have shown its formation, but recall that the driving force for the Claisen condensation, these series of steps with equilibrium constants less than 1, the driving force was this final, really favorable deprotonation of the beta ketoester at that doubly alpha carbon, right? It's alpha to 2 carbonyls. Now, in the case of this product of the Claisen condensation, the doubly alpha carbon doesn't have any alpha CHs, right? There are no CHs on that doubly alpha carbon, so it cannot be deprotonated. Thus, the overall equilibrium constant for this proposed Claisen is less than 1. And so this product cannot be isolated. Even though it's formed in small concentrations and cannot be isolated. All right, bummer. Does that mean we can't make it? No, it does not. We'll just need another way. But we cannot make this product by a Claisen condensation. So that's just the point here. So the product, whatever the beta ketoester is, it must be analyzable for the Claisen reaction to occur. And that just means it must have a doubly alpha CH. Just like in the previous question, this proposed beta ketoester, it had alpha CHs. Because of that, this stable enolate could be formed, and this Claisen did occur. That is not the case in this problem. So this beta ketoester cannot be formed by a Claisen. So that's right, that cannot be isolated via a Claisen condensation. But, some foreshadowing, we'll figure out another way to make this product. Excellent. So just thinking about the aldol reaction and the analogies between the Claisen and the aldol. For aldol, we had that self-condensation. We had a cross condensation. So self was when the enolate and the aldehyde came from the same molecule. So the acid aldehyde enolate condensed with the neutral compound of acid aldehyde, for example. The cross aldol is when the enolate and the electrophile, the neutral compound, come from different molecules. So we saw using, say, acetophenone, so a ketone enolate, with an aldehyde, such as benzaldehyde. And then we had an intramolecular variant for the aldol as well. And we'll see that with the Claisen in just a moment. But for now, let's look at the crossed Claisen condensation. So we'll provide a complete curved error mechanism for this transformation. So pause and give it a shot because you know how to do this now. It'll be really good practice for you. Just pull up your notes from these 2 slides. All right, give it a go. When this ester is treated with diethyl carbonate in the presence of sodium ethoxide, again, noticing that the alkoxy group is kept constant to avoid transesterification in the product. This beta diester is observed. Right? There's this 1,3 relationship between the carbonyl groups, and we see there's a doubly alpha carbon that does have a proton on it. So that product is enolizable, so I bet it comes from a Claisen condensation. Thinking about what bond was made overall before we even get started, it looks like it was this 2,3 bond, and that these 3 carbons came from ethyl propionate. Only this ester is alpha enolizable, so only this ester will react with the sodium ethoxide, which really reminds me of the cross-aldol reaction in which only one of the 2 aldehydes or ketones that reacted with each other were alpha enolizable. So in this case, between the ketone and benzaldehyde, only the ketone was alpha enolizable. And that's what we see here as well. Only one of these esters is enolizable. So that generates this ester enolate, even though the equilibrium constant is less than 1, much less than 1, it is still generated in appreciable concentrations, or at least enough to continue reacting. So it is going to react with the diethyl carbonate in a nucleophile addition step. That nucleophile addition step generates the key carbon-carbon bond. There it is. And we'll fill in everything else here. Here's a carbonyl carbon of diethyl carbonate. Now this tetrahedral intermediate will collapse, expel one of the 2 possibilities, right? Both ethoxides are good leaving groups. So it will collapse and expel ethoxide. Either one is fine in this nucleophile elimination step, generating this beta diester. However, of course, under these conditions, in the presence of ethoxide, the beta diester is deprotonated. This proton transfer reaction has an equilibrium constant of about 10 to the 3, so it's much greater than 1. This proton transfer step does represent the driving force for this Claisen condensation. In the workup, the enolate is protonated to generate the final beta diester product. This cross-Claisen condensation between 2 different esters followed the same series of steps as the self-condensation. The key was that only one of these esters was enolizable. I have one more example of a cross-Claisen condensation for you to try on your own. I'm not going to explain the answer on this video. As we said with the aldol, there were self, crossed, and intramolecular versions, and the Claisen will be no different. So this is an example of an intramolecular Claisen condensation. One other difference you can see is sodium methoxide is used instead of ethoxide as the base. And again, that is to avoid transesterification. So a different alkoxy group in the reactant, different alkoxy group used to deprotonate. So go ahead and provide a complete curved error mechanism for this transformation, and then we'll compare together. The alkoxide base deprotonates either alpha carbon. They are the same. This molecule is symmetrical. This proton transfer step generates a molecule that has an electron-rich ester enolate and a neutral ester in the same molecule. So they're going to react together, making this an intramolecular reaction. The alpha carbon of the enolate is going to make a bond to the carbonyl carbon of the neutral ester. This occurs in a nucleophile addition step. To determine the ring size, number between the 2 carbons that are making a bond, in this case the alpha carbon and the carbonyl carbon. So make a 6-membered ring. This nucleophile addition step generates the tetrahedral intermediate shown. We can see formation of this key carbon-carbon bond. This tetrahedral intermediate contains a leaving group, that is methoxide. On pair push, reform the strong carbonyl CO double bond in a nucleophile elimination step and expel the methoxide leaving group. This step forms this beta keto ester that is enolizable and is immediately deprotonated by methoxide to generate the nice stable doubly alpha enolate. This enolate can be reprotonated upon acidic workup to generate the neutral product. And again, we see this beta ketoester, and it tells us that a Claisen condensation has occurred. Oh, we've done it. We've done intramolecular, crust, and self-Claisen condensations. Now I'm going to show you one more amazing and terrific reaction that we can couple with the Claisen condensation, and that is a decarboxylation. Don't worry, I don't expect you to provide a complete curved error mechanism without me, so let's do this together. We see we have a beta ketoester, and in the product, that ester is gone. Poof, where did it go? Well, let's figure that out now. When an ester is treated with sodium hydroxide, what happens? Yes, an acyl transfer reaction occurs. Initially, the carboxylic acid is formed by a nucleophile addition elimination process, but then that will be immediately deprotonated to make carboxylate. So we learned this in the acyl transfer class. And that's what happens here as well. So hydroxide can add to either the ester or to the ketone. But when it adds to the ketone, nothing can happen except it just gets eliminated because the ketone doesn't have a leaving group. So the productive pathway here is the hydroxide adding to the ester to form a tetrahedral intermediate that does in fact have a leaving group. This tetrahedral intermediate could collapse, it could expel hydroxide to go back up to the starting material, or it could expel ethoxide and productively move us along this pathway to generate this beta keto acid. So the ester has been converted to an acid. Of course, we are in the presence of hydroxide, and the acid hydrogen has a pKa of about 5. So a proton transfer reaction does occur, which generates this carboxylate intermediate. Okay, so now we're really just at an acyl transfer reaction, and we've learned that previously. So that was step 1. Now, step 2, treat with acid and heat. So when we treat this with acid, it's like, kind of feels like an acid workup, right? Because that just generates the carboxylic acid. And now I'm going to rotate around this bond so I can better show you what happens next. So what happens next is that the hydrogen of the acid is accepted by the beta keto group. The electrons in the OH bond come down and make a CO double bond here. And then the electrons in this bond between the alpha carbon and the acid carbonyl, they go here. And what is generated is an enol and a molecule of CO2, which floats away. CO2, and there's that hydrogen, it's here. There's the alpha carbon. All right, and how is this ketone product formed? Well, just the keto-enol tautomerization. You already know the mechanism for that, which you can draw out. It's under acidic conditions. All right, poof, gone. The ester group was converted to an acid. So ester to an acid under acyl transfer conditions. And then when it was heated, and this is really key, the poof part, this is what's called a pericyclic reaction. And we'll learn them later in the semester, but this part really does require heat. CO2 is actually eliminated. Nice stable molecule bubbles away, really essentially irreversible, and the equilibrium is driven by Le Chatelier's principle. All right, cool. So this was awesome. Well, why is it important? We'll get to why this reaction is so important in just a minute, this decarboxylation, why it's so important in just a minute. But before we do, I just want to be clear, we cannot just poof, remove ester groups willy-nilly. It has to be beta to another carbonyl. And that's because the electrons in this bond between the alpha carbon and the carbonyl of the acid, those electrons have to go somewhere, right? And they need to go somewhere stable. Also, this proton needs to go somewhere, so there must be a proton acceptor. So the carbonyl can accept the proton, and then these electrons and this bond between the CO2 carbon, what becomes a CO2 carbon, and the alpha carbon, they can go and make the enol. So formation of this enol, a place for the hydrogen to go and the electrons to go, it really is key to the decarboxylation happening. Otherwise, the decarboxylation is not going to happen. So you cannot have random ester groups just turn to carboxylic acids and poof, disappearing. It has to be in the contacts of these 1,3-dicarbonyl compounds. Now let's see why this decarboxylation is so important. We have learned that enolate ions can be good nucleophiles in the SN2 reaction, but not under equilibrium conditions. And what that means is that they need to be quantitatively generated in order to be used in SN2 reactions. So just a normal aldehyde or ketone, as we've said, if it's treated with an alkoxide base, the equilibrium constant for formation of the enolate is less than 1. And so what that means is that alkoxide bases cannot be used to generate enolate ions for SN2 reactions. Can be used for aldol and things, but not for SN2. So for SN2, we actually had to use LDA to quantitatively generate the enolate and then do stuff with it. Now, if we think about a beta diester or beta ketoester, the pKa of the doubly alpha carbon is much, much lower than that of a normal ketone. And so when it is treated with an alkoxide base, the enolate is essentially quantitatively generated because the equilibrium constant is much greater than 1. And now this enolate is an excellent nucleophile in SN2 reactions. Reform the strong carbonyl, attack the alkyl halide in an SN2 reaction, and generate this alpha-alkylated product. So that's cool. These 1,3-dicarbonyl compounds can be converted to enolates under pretty mild conditions, alkoxide bases, and then alkylated in an SN2 reaction. With just normal ketones, this required LDA, which we know is not mild. Now that we've introduced how these 1,3-dicarbonyl compounds can be excellent nucleophiles in the SN2 reaction, it's your turn to provide a complete curved arrow mechanism for this transformation. In the presence of an alkoxide base, such as methoxide, the doubly alpha carbon is deprotonated. This proton transfer reaction yields a stable enolate shown and an equivalent of methanol. Based on the pKa's of the product and reactant acids, the equilibrium constant for this step is on the order of 10 to the 5. The enolate of the 1,3-dicarbonyl compound, the beta ketoester, is an excellent nucleophile. When treated with ethyl bromide, the carbonyl is reformed, lone pair push, pushing those electrons between the two carbons of the enolate to make a bond on the alpha carbon and the electrophilic carbon of the alkyl halide. This SN2 reaction generates this desired product. Let's think a bit more about that beta ketoester, because beta ketoesters can be formed by Claisen condensations. So yes, we just formed this desired product by an alpha-alkylation, but perhaps we could imagine that an intramolecular Claisen could be used to form the same desired product, where the ester enolate would attack a molecule of the neutral ester serving as the electrophile, and the ester enolate serving as a nucleophile. So the key carbon-carbon bond forming step would look like this, and generate the 6-membered ring shown. Looks reasonable, right? Actually, this product will be formed, but in really small amounts, and it will not be possible to isolate it in high yield. So this will not work. And do you remember why that is? Yes, that's because the doubly alpha carbon of the beta ketoester formed in the Claisen condensation must be alpha enolizable. Because as we discussed, this last proton transfer step is the driving force for a series of unfavorable equilibria and allows the beta ketoester to be generated after workup. Okay, so this molecule cannot be generated directly by a Claisen, but it could be made by an alpha-alkylation. But again, we don't want to get too carried away and start to alpha-alkylate everything in sight. For example, we've discussed this sequence, which would not work. The sequence would not work because the enolate proposed would be formed with the equilibrium constant less than 1, so it'd be present in small concentrations. And plus, if we mix together sodium methoxide and methyl iodide, well, they're immediately going to react themselves in an SN2 reaction to form dimethyl ether. Yikes, that was not desired. Well, there is a solution to this, and it's using the power of the doubly alpha carbon, so the power of the beta ketoester. We're going to synthesize the same desired product as we had on this slide, right? And we're going to start from the same starting material. We're going to start from cyclohexanone. So same desired product, same starting material, but we're going to take a different approach. So first, we'll propose a Claisen condensation. And this is one of those cross Claisens between a ketone enolate and the diethyl carbonate. I'll quickly draw the mechanism, but you could always try it on your own first. The enolate product of this proton transfer reaction, although formed with an equilibrium constant less than 1, is still nucleophilic and will react with the diethyl carbonate, which is electrophilic at that carbonyl carbon, and they react in a nucleophile addition. And this is what we would expect for a polar pi bond. And hopefully we also recognize that this is a Claisen and we're applying what we know about how these types of starting materials interact. This tetrahedral intermediate collapses to expel an equivalent of F oxide. The carbonyl is regenerated. The doubly alpha carbon has returned. Right now this alpha carbon is alpha to 2 carbonyls, and a molecule of F oxide is formed. Now, F oxide, either the molecule expelled or another molecule in solution, because F oxide is present as a reagent, will deprotonate the doubly alpha carbon to generate this stable enolate. This step is, again, the driving force of the Claisen condensation with an equilibrium constant on the order of about 10 to the 5. So after step 1, this is where we are. And typically we would employ a workup to protonate the doubly alpha carbon and yield the neutral 1,3 dicarbonyl compound, the beta-keto ester. However, in this case, we would like to install the methyl group. We know that the methyl group is installed by an alpha-alkylation on the enolate, so why not just use the enolate directly rather than working up? Since it's electron-rich at the alpha carbon, it's nucleophilic. So that's what we'll do. We'll treat with methyl iodide. The strong carbonyl reforms. The alpha carbon reacts with the methyl carbon of methyl iodide. It's electrophilic, expelling the good leaving group and making this carbon-carbon bond that we see in the product. All right, awesome. So the alpha-alkylation of the beta-keto ester was successful, whereas the alpha-alkylation of the ketone was not successful. Just recalling this slide, right? So we could not install the methyl group directly to the ketone. We could have using LDA, but using alkoxide bases, that was not possible. But with a Claisen condensation, so basically making the really nucleophilic enolate by undergoing this cross Claisen, generating the beta-keto ester, that allowed a quite facile alpha-alkylation to install the desired methyl group. Now the problem is, sort of problem, that we have this ester group that was installed that is undesired. So we used it to make the alpha carbon really acidic and nucleophilic, but it's not desired in the product. So no problem, it will be removed in a decarboxylation sequence. So step 1 is that acyl transfer, the hydrolysis, to generate the carboxylate. And then in step 2, the carboxylate is protonated to form, oops, forgot the methyl group, sorry, is protonated to form the neutral acid, which undergoes decarboxylation. And poof, generates the desired product, which I have written all over, but it has been generated. Took us 2 slides, 2 different synthetic routes, but it has been generated. And if you need to look at the mechanisms for the acyl transfer, the decarboxylation, we have written those out on a previous slide. Now here it is. So you can go back and review that slide. So as you can imagine, this is a tough sequence to recognize in a synthesis problem because the Claisen condensation installs this ester, beta to the ketone, and then it's also removed by the end. So you have to recognize, hey, this alkylation could not happen unless there was a beta-keto ester. All right, now it's your turn. So one of your classmates proposes the following alkylation. List 2 reasons why the synthetic scheme would be unsuccessful, and then propose an alternative route to the desired product from the given starting material. So you still need to go from this starting material to this product. Give it a shot. Be sure that you try this problem on your own first, at least to list the 2 reasons why the scheme will be unsuccessful. And those reasons are that the equilibrium for forming the enolate does not favor the enolate. And although that doesn't matter for Claisen, it does really matter for alpha alkylations So for alpha alkylations, the enolate needs to be made 100%. And with an alkoxide base, the equilibrium constant is much less than 1. So that's one reason this doesn't work. The second is that if you look at the desired product, actually, here's where the carbon-carbon bond is formed, and the kinetic enolate is required. So we already knew that we needed to use a Claisen scheme, so that's fine. The only tricky part is that we need to generate a beta-keto ester that looks like this. And then the choice of what the alkoxy group is doesn't matter. I'm just using methoxide or ethoxide. You needed to make the bond here in the Claisen, so that would require the kinetic enolate. And that's not what's going to happen if you just take this and you treat with sodium ethoxide and diethyl carbonate. Alkoxide bases deprotonate to make the thermodynamic enolate, so when the Claisen occurs, that carbon-carbon bond is formed, and you can work that mechanism out on your own or ask me for help. However, we need to form a bond between alpha prime, the less substituted alpha carbon, and the diethyl carbonate. And that's no big deal. So we're just going to deprotonate first with LDA at low temperatures to generate the kinetic enolate. Once the kinetic enolate is generated with LDA, it can be treated with diethyl carbonate to generate the beta-keto ester. We're going to delete the alphas because now there's only one alpha carbon we care about, the doubly alpha carbon. Now this is acidic at the alpha carbon with a pKa of about 11. So now we can deprotonate and treat with a desired alkyl halide. Deprotonation will generate the enolate, which will react in an SN2 reaction with the alkyl halide as we discussed on the previous slide. This sequence yields this product, which is very close to the desired product. All that's left to do is remove the ester group. It will be removed first by generating the carboxylate in an acyl transfer reaction, then treating with an acid source and heat for the decarboxylation. Great, so now you can use Claisen condensation and alpha-alkylation of the doubly alpha carbon to solve alkylation problems. Excellent. Before we end this video, I just want to remind you that you have already learned that beta-keto esters, such as this one, can participate in the Michael reaction. So now you know that a workup would be needed. Now you can imagine this Michael product could be decarboxylated. Poof. And so all kinds of fun synthesis problems are in store for us. So just be sure that you review the Michael reaction since they also involve beta-keto esters. So this is just a conjugate addition. Let's look back at our reaction chart. Here it is. My magic, here it is filled out. Just keep in mind as we're doing our brief rundown of these reactions, this is all about alpha carbon chemistry, mostly applied to esters and a little bit to carboxylic acids, but this is all about alpha carbon chemistry. We've learned a lot about alpha carbon chemistry in the past. We learned about enols, enolates, aldol reactions. So this is building on what we know about the reactivity of the alpha carbon. Let's start with the haloform reaction. So the haloform reaction made methyl into a good leaving group. Broke this bond, generates carboxylic acids from methyl ketones. The Hell-Volhard-Zelinsky reaction, alpha brominated carboxylic acids to generate alpha bromo acids, which can then be used to do fun things like make alpha amino acids if bromine is substituted for the amino group. In the Claisen condensation, an ester is converted to an enolate and reacts with the neutral molecule of itself to generate these beta-keto esters. We saw a couple of variants of the Claisen condensation that I don't have written down here, but you should be sure to write down yourself. So there's also the intramolecular version. There's the crossed version, including we looked at some examples of using ketones plus ethyl dicarbonate to generate beta-keto esters. So please be sure that you recognize the Claisen in all of its forms. Now, these beta-keto esters or these 1,3-dicarbonyl compounds are super useful because they have the magical doubly alpha carbon. And that doubly alpha carbon is quite acidic. And then also once it's been converted into the enolate, makes for an excellent nucleophile and can be alkylated in SN2 reactions with alkyl halides such as alkyl bromides, which I've shown here. When alkoxide bases are used, we match them to the alkoxy groups of the ester just so there's no transesterification. We see that in the Claisen above as well. Check out the carbon-carbon bonds that are made Remember, organic compounds are made out of carbon, so anytime a carbon-carbon bond can be formed, especially in these mild conditions, that's a good thing. So I've shown two examples, beta diesters or beta ketoesters. We could also imagine diketones being used in this alkylation reaction as well, okay? So any of these 1,3 dicarbonyl compounds can be alpha-alkylated in this way because of the special acidity of the doubly alpha carbon. It's alpha to 2 carbonyls. Finally, the products of these alpha-alkylations can be decarboxylated to remove one of the ester groups. So in the case of the diester, in this first step, both of the esters are hydrolyzed to generate the carboxylates. They're both protonated in the second step to form the carboxylic acids, but only one of them leaves. So the other one, the one that doesn't leave, this one is left as the carboxylic acid after the decarboxylation. In the case of the beta-ketoester, the ester group is converted to a carboxylate in step 1, back to the acid in step 2, and then decarboxylated with the heat. Poof. I reminded you of conjugate additions of enolates of these 1,3-dicarbonyl compounds, such as the beta-ketoester, or even the beta-diester could do this, right? And you can review that from previous lessons. We'll learn the Gabriel synthesis in a later video. This is quite enough for now. It's time for you to practice once you have summarized. The second question is particularly relevant today. All of these reactions relate to previous classes in some way. Haloform versus Baeyer-Villiger, alpha carbon chemistry, so the aldol version of, the ester version of the aldol reaction, the Claisen condensation, etc. I'll let you think about whether or not you've met the learning goals on your own, and then let me know if you have any questions.